Hey guys, so we continue down here in the basement as Dr. Mom continues to do this online lessons, becoming an online professor because of coronavirus. So let's get on with the independent t-test. So the independent t-test has specifically to do with what? It has to do with two independent samples. That's why it was called the between subject t-test. It was called the two samples t-test because we're looking at two samples. So let's do what we did before. Let's keep in mind our formula as we're running through the 4 steps of hypothesis testing. So first we're going to have the mean of one sample minus the mean of the other sample minus the mu and the mu1 and mu2, the population of each of these samples. And think about it. Is there a significant difference between the two samples? The HO tells you there is not a significant difference. The samples that we're testing is hoping that they find a significant difference. So in reality, do we even need this part of the formula? Mu1 minus mu2. We actually don't, because there is no significant difference between the two populations. That is HO. It comes out to be 0. So this would be minus 0. We don't have to write it. Where we're actually testing the difference is if in the samples they're going to tell us that there is a significant difference amongst these populations. Because in reality, we're saying that there's not with our null hypothesis. So we actually only need to write this piece of the formula, the mean difference between these two samples. The bottom of the formula, once again, also gets doubled, right, with this SM1 minus M2, right? We're talking about the difference between two samples. So we're talking about the bottom of the formula is estimated standard error, and the bottom of the formula is simply doubled. We simply go the variance of the first plus the variance of the second, right? And we square root the entire thing, because this stands for the combined variance of both of them tested against the difference between the two samples. So this is truly our formula. Let's keep it in mind as we go through the problem. So let's hear the problem, and then once again, just like I've said before, the easiest way to ever attack word problems is pull the data. So researchers investigated the influence of background noise on classroom performance for children ages 10 to 12 years old. In one part of the study, calming music led to better performance on math tests compared to non-music classrooms. Suppose the researcher chose one of the classrooms of 18 students and served them as the control group, and then had another classroom of another 18 students where they had no music and had the experimental group. The two actual test scores for both of the groups were measured. And for the first group, where we had music group, it yielded a mean of 86.4 with a sum of squares of 1550, compared to the control group with a mean of 78.8 and a sum of squares of 1204. Is there a significant difference between the groups at a 5% level of significance or an alpha level of 0.05? Before we jump in, if you were listening and seen some of my other tutoring and lectures, you've realized that I haven't talked too much about the sum of squares. This was taught in previous chapters throughout my lessons before coronavirus told me all of a sudden I had to go online. So there's probably no videos about sum of squares yet, but there will be. So let's quickly recap for those that haven't seen that piece or don't remember that piece or didn't really get that piece originally, that there's a relationship between the sum of squares, between the standard deviation, and between the variance. So let's recap it real quick. So what do you need to get each one of these? If we're talking about the variance, how do you get the variance? If we're talking about the standard deviation, we use the variance to get the standard deviation. So the variance is used how? It is the square root. So take the square root of the variance, or s squared, will give you a standard deviation. How do you get the variance? Well, the variance is the sum of squares over the degrees of freedom. And what was the sum of squares? The sum of squares was essentially the sum of the deviation scores squared. Now, all that might seem a little like, what? Well, think about it. To get an average, we basically said, everyone tell me your score. Let's say on a test. We took everyone's individual raw score, added them up, and divided by how many we had. We got the average. Then we asked every person, how close or far are you from the average? And took all those new distances, or what we call deviations, and added them all up and divided by how many you had, giving us a standard deviation, because that's the process. But when we did that process, we realize that the mean is going to balance. So if we ask every person how far above and how far below you are from the average, it's going to lead to a normal distribution. Perfection. It will lead to a balance. It will lead to 0. So how are we going to have an actual standard deviation? How will we divide everyone's distance by how many people we actually asked if the conclusion of everyone's distance, once we add them all up, came out to 0? 0 divided by anything is 0. So then what did we have to do? We had to then double all the scores. Ask every person your distance from the mean, and whatever their answers were, we doubled them to get rid of the negatives. So we get rid of the idea that it balanced. And adding up all those scores led to the sum of the squared scores, hence the sum of squares. And the sum of squares, these squared scores added up, divided by how many you had, not just n, the sample size, the restricted sample size, so n minus 1, in other words, divided by degrees of freedom, gave us the variance. And the variance then, the square root of it, if you doubled to get rid of your issue of the balancing, the deviation scores equaling 0, the only way you can come back from a double is to square root. If you doubled it or squared it to get there, the only way to get back down from this whole process is to square root it. Eventually, I will do a video on standard deviation, and you guys will be able to see that whole process work out. But in this problem, we're going to start with the sum of squares, which is going to lead us to the rest of these numbers that we need to fill in our formula. Okay. So let's do this. Once again, remember, we're talking about the classroom in music. Those that have music in the classroom versus those that do not have music in the classroom, and how they do on tests. So we're going to have two independent groups from each other. That's what the homogeneity and variance has also told us, which leads to a final assumption inside of the independent t-test and requirement for the independent t-test. Each person can only be measured once. They have to be independent of each other. If a person was measured twice, like you double dipped, you love chocolate and strawberry, nope. You gotta love one or the other. So each person was measured independent of each other, and we're not measuring each of the groups twice. So if we pull the information for the first sample, right, we're gonna have the first sample's mean, the first sample's size, the first sample's sum of squares. Then we're gonna have the second sample, well, actually we'll put it here, the second sample's mean, the second sample's size, and the second sample's sum of squares. We know the alpha level is 0.05, and once we read it, we'll decide how many tails we have, right? 2 tails or 1. Are we looking at a significant difference saying one is better than the other, or are we just simply looking for a difference amongst the two groups? Music versus no music. So if we look at the first group, and the first group of students, essentially, we're looking at the students measured for all the music group. All right, so let's look at music. All right, so the music group gave us a mean of 86.4. And the sample was 18 students. And the sum of squares for that one was 1550. And the second group of non-music was 78.8. And there was also 18 students, and the sum of squares for them was 1204. And what are we simply asking? Is there a significant difference between using classroom music and using non-classroom music in terms of testing for math? So all we want to know is there a difference? We're not saying one's better than the other, so we have a two-tailed non-directional test. All right, 2 tails. And remember, this information is needed to do what? To think about your actual step 2, setting the criteria. The only piece we're missing here is setting our degrees of freedom, which just like in the other test, if we had 1 degrees of freedom for 1 n, here we have 2 m's, 2 n's, so our formula also is going to have to be doubled. Our degrees of freedom then is not just going to be n minus 1, it's going to be n minus 1 for each of the sample groups. So in other words, the first sample group minus 1 plus the second sample group minus 1. And then we'll find the answer to our degrees of freedom. So essentially, this is going to be part of step 2. So going into step 1, we're going to have 2 hypotheses just like we did before. And remember, our hypothesis has to reflect our population's means, right? And it also has to reflect how many means we actually have. 2, right? Because 2 groups. So mu1 minus mu2 equals 0, right? Because the null hypothesis says there is no difference between the mean of each of these populations. And the alternative hypothesis for us is saying there is a difference between classroom music and not music. I don't know where, but I'm just saying there's a difference. So I'm saying it would not equal 0. In other words, I would find a difference somewhere. So that is our step 1. When we go into step 2 is setting our criteria. Well, here's our alpha level, there's our criteria. How many tails we have? That's 2, there's our criteria. Our degrees of freedom. So we have 0.05, right? We have 2 tails. And what's the next thing we have? Degrees of freedom. So our degrees of freedom equals 18 minus 1 plus 18 minus 1. In other words, 17 plus 17 equals 34. All right, so hopefully you're all with me at this point and none of you guys have gotten lost. So if we're looking at our degrees of freedom, we have our tails. We can look in the back of the book and we can find out our T critical. And if we get our T critical, we're going to realize it's going to be what? It's positive and negative because remember we have 2 tails that can be on either side. When we look it up, it came out to 0.0 to 2.021. Now what do? Step 3, the fun part that everybody loves. In other words, plug in all the numbers into the formula and run your actual test. This is the part that everyone likes to do because they're like, this is the part we truly understand the most. So in other words, plug in the numbers that we're going to do. The mean of sample 1 minus the mean of sample 2, and then the variances or the sum of squares. Remember, we started with sum of squares. So we actually first have to calculate variances for each of these before we can even plug it into the formula, right? So let's start off with the top. The mean, 86.4, minus the other mean, 78.8, over. Remember, we have sum of squares here. So the sum of squares and degrees of freedom for the first, the sum of squares and degrees of freedom for the second. So what was the first sum of squares? 1550. What was the second one? 1204. And what was the degrees of freedom for each of them? 17 and 17. And what will this give us? This will give us the variance for each of them, right? And so when we calculate the variance for each of them, we are actually going to come out and calculate 9118, and we're going to get 7082. Right? When we actually calculate these out, these are going to be our numbers. So now we can plug in these variances into the formula, the variances of each, the sample sizes of each, and then of course, remember, sample size is 18, degrees of freedom is 17. Don't get yourself confused. So let's do this, right? 9118 over 18 plus 7082 over 18. And when we figure this out, we have to square root the entire piece of the formula. And so when we figure this whole beautiful thing out by getting all these beautiful numbers, this whole thing is going to lead us to 3, right? This whole mathematical, right? 9118 divided by 18, 70 divided by 18, 2 values, add those numbers up, is going to lead us to the bottom of the equation as a 3. And the top of the equation, 86.4 and 78.8, essentially is going to lead us to 7.6. And 7.6 divided by 3 leads us to a T statistic of 2.53. That is the value we got at the end. And when we do that, how do we do step 4 again? So step 3 gets compared back to step 2, which gets compared back to step 1, which then leads us to step 4. So let's decide. Do we have a significant difference amongst the 2 groups in terms of music impacting test taking? Is 253, 2.53, bigger than 2.021? Yes. So in other words, music did impact the way the students tested. So step 4 would basically B, make your decision. And you would have to write it out, right, with the T. So just for spacing, let me erase the formula so that you can see what it would look like when you write it out. So remember, you have to have the degrees of freedom, which we concluded was 34. You have to have the value, 253, and you have the p-value. Are we greater than or less than 0.05? We are less than 0.05, which means I landed in the actual tail, and we found a significant difference. So this actual reading, or these numbers, go to the back of the sentence or the end of the conclusion of that one section in the actual research article that we'd all love to skip, which is the methodology section. And we see all these symbols and numbers and don't understand what they mean. But hopefully now they make a little bit more sense. Thanks.